And Maryam's done just really amazing work spanning all the way from very theoretical topics and signal processing, compressed sensing, optimization, and machine learning to all kinds of really nice applications of this work across all these different areas, and has collaborations, I'm sure, with quite a few people in the room. So I'm excited to hear about the newest work a little more theoretical level. Thanks.
Thank you. Hi everyone, and thanks to Luke for inviting me to talk in this seminar. I really look forward to hear any feedback you guys have about what we're going to talk about. It's a little bit of an abstract topic, but appears to have connections in different areas in machine learning, and I'm hoping that you guys will also help find those connections and tell me afterwards if you have seen anything like this. So I'll be talking about recovery of models with simultaneous structures. This is joint work with my student Maryam, who's actually right there. And he's the one doing all the work, especially the plots I'm going to show at the end. Also, we have collaborators at Caltech, Samet Oymak, who's a student there, and Professor Babar Kasibi. And we have had also input from Professor Yonina Eldar at Tech. Okay, so what are structured models? Essentially, what I mean by this in very broad sense is that models that have a low-dimensional structure but live in high-dimensional ambient space. So, for example, you're looking at a vector that is in n-dimensional space, so size n vector, but it has a lot of zeros in it. It has only, for example, k non-zero entries. So the actual degrees of freedom or the information contained in that vector is on the order of k, whereas the ambient dimension is n. So I'll be interested in that kind of models, inherently low-dimensional but living in a high-dimensional space. And then the type of problems we consider about such models are recovery or derivation of such models from limited observations. So we want to see if we have only limited information about an object or model or signal, can we find it, and how should we go about finding it? Such problems in this very abstract setting arise in signal processing, and I'll give some examples, in machine learning and in the control area of system identification, where you want to identify dynamical system given inputs and outputs information. And the typical questions are, at least from my point of view, the very typical question is, can we construct convex penalties, or known in machine learning as regularizing functions or regularizers, that would promote the type of structure that you want in the solution you're looking for. So basically, I'm going to pose this as an optimization problem, and the critical point is the convex penalties that arise in that optimization. And once you write down an optimization problem, how can we quantify the performance? So what are some typical examples? The one I just mentioned, sparse vectors. A vector in a very huge dimensional space, but has lots of zeros, very few non-zero entries. And this object has given rise to and basically the ability to sense and recover such objects successfully gave rise to the area of compressed sensing, and there are lots and lots of references. So these are just like one representative reference of each of these topics. It's been used in the area of, or in problems called lasso, that goes back to Kipchirani's work in '96. There's lots and lots of variations on it. It's also heavily used in image processing, especially denoising. These structures come up because, for example, a lot of natural images have a sparse representation in the certain Fourier domain or wavelength domain and so on. They also, in other interesting structures beyond sparse vectors are, for example, block sparse or group-sparse vectors, in which you still have a vector in high dimensions with lots of zeros. But the zeros now have some structure. They come in groups, for example. An example of that is group lasso, but there's lots and lots, again, of variations on these kinds of signals or objects. Another kind of object of the same category that I'm particularly interested in is a matrix that has a low rank. That problem comes up, problems of recovery of this object come up in, for example, collaborative filtering, things like Netflix problem, for instance, where you have a large database, and you have some entries in that database observed, and the rest are not known, and you would like to fill them in. A problem known as the matrix completion problem. With the assumption that the underlying database matrix tends to have a low rank, or is close to low rank, then there are some results on that problem. And, well, results are in these papers and further papers. Same problem of low rank matrix recovery comes up in system identification in control, where we deal with the rank of a Hanko matrix that captures the mapping between inputs and outputs of linear dynamical systems. A newer set of problems of this class or set of structures that people consider are sparse plus low rank matrices. So in this class, you actually have a combination of two of these node structures, for example, sparse and low rank. But the object that you're interested in is the summation of a sparse part and a low rank part. So there's a plus between this part and this part. And this problem comes up in principal component analysis, where you have the matrix you want to find principal components of has been corrupted by outliers. So sparse outliers in principal component analysis. It also comes up in certain graphical models problems, for example, where you have hidden unobserved variables that correspond to a low-rank part of your inverse covariance matrix plus a sparse part of inverse covariance matrix that corresponds to the graph being sparse. Okay, so these are some examples. I'm going to now talk about two newer examples, or basically types of structures that haven't been so much considered before. So these have all been studied well. So the new ones I'm going to consider in this talk are the following. One is that, well, the object I may be interested in might be a matrix that is simultaneously sparse and low rank. So it's different than this one. It's not the sum of two parts, but the matrix has simultaneously two properties, or two different structures. And this comes up in, for example, signal processing application of signal phase retrieval. I'll be talking about this more later. And another one is actually in the graphical models again, for example, sparse inverse covariance matrices. And so sparse inverse covariance matrices have been used a lot. That falls under this category. But suppose I have further structure in that in the inverse covariance matrix. For example, one that we have worked on very recently. This is joint work with Daniela and Suin and Karthik who are here. And this one involves finding inverse covariance matrix corresponding to a graphical model that is both sparse and row-column sparse. It's a particularly structured part of structure. And the graph has both of these properties. The network has both these properties at the same time. So in that sense, it's an example of a simultaneous structure. Okay, any questions? So I'm going to talk about this category of signals or objects and how to recover them. What do we mean by recovering signals? So this comes from signal processing terminology, by the way, and don't worry, you can translate everything into machine learning if you want. I'll show you later kind of how. But I'm going to be talking about signal and measuring them and recovering them, but again, it's the same thing as being given some information about the model and knowing some structure, prior structure about the model and wanting to construct the model. Okay, so in the signal processing language, you would say the following. The basic setup is, I have a structured object, red object, like x, for example, I denote it by x naught in general. It comes from some vector space. And I have linear observations. I'm given linear observations of that object. So it means something like this. Linear operator g that goes from Rn to Rm, acts on x naught and gives me y. So that means the dimension of y is m. I have m linear measurements or observations of the object. And typically, m is much, much less than n. So I have an underdetermined system. That's where the prior knowledge comes in, and I want to recover x naught. So the goal is this: given y and the structure, find x naught. So a lot of research has gone into basically this setup applied to the different structures I discussed. Typically, people ask two questions. One is how to recover the desired model efficiently. Efficiently means you have to give a tractable numerical or computational method to find it. And also a theoretical question: how many generic measurements suffice? How small can m be? Which is actually of importance both information theoretically and practically. How much information inherently is in your signal, and how much you can compress that object and yet be able to recover it. In these settings, we are looking at exact measurements. There's no noise in here. However, it's usually not hard to extend them to noisy observations. Also, we are assuming our object is exactly structured. It belongs exactly to the class that we know. But it could also be nearly structured. So for example, a signal can be nearly sparse, or a matrix can be nearly low rank. Usually results also extend to these non-ideal situations. Okay, so one more thing. I mentioned generic measurements, so what do we mean by generic? At least for the purpose of this talk, I mean something very specific, which means that if I look at that measurement operator G, since we are dealing with finite dimensions, I can represent this with a matrix, so it becomes an m by n matrix. I will assume that the matrix has entries that are random, IID, independent, and identity distributed Gaussian entries. Which means the matrix that I pick, the G I pick randomly. And the reason to do that, at least one justification to do that, is that we want to find estimates on M, on the number of measurements, that work for a very large class of measurements, of M by N matrices. And basically, if you want to state something about all M by N matrices, a good way is to create a closed, dense subset of that set. And this is one way to do that. Then you can say something with high probability holds for such measurements. So that's what we mean by generic measurements. It's a very common setup in compression and compressed sensing question.
Is the measurement matrix known?
Yes. In fact, oftentimes you're actually designing that as well, at least in signal processing. That's your signal acquisition process, and often you can somewhat design that. In some other applications, you cannot design it, but it's so. So our unknown is only the x. So in the constraint, this is a linear equality constraint on the unknown that I want to find. I know g and I know y. So given y and of course g, find x. Okay. So typical example. So this one is probably very familiar. I'll go over it really fast. I want to find a k-sparse vector. So sorry, k here is the sparsity of the vector I want to find. So x0 is the vector I want to find. Gx0 are the measurements corresponding to that vector. And here I want to solve this optimization problem over x. And card x means cardinality, the number of non-zero entries, because I know the number of non-zero entries are small. If I am able to solve this optimization problem, how many measurements do I need? How many constraints I need? What is the size of the G? For this, to be able to uniquely identify the correct x0. This question has been answered well, probably has been answered for a long time. It's not that hard. You can do it by dimension counting. And the answer is this: why k log n over k number of measurements are enough. They identify the k-sparse solution uniquely in a subspace of solutions. Right? So probably you have seen something similar to that. K log n before. However, what was newer, like started in maybe late 90s and early 2000, and especially 2004 work of Donoghue and Candes, is that it turns out this problem, which is, well, by the way, this one is not a convex problem. Cardinality is a non-convex function. It's horrible. It's an integer value, really bad function. You can't even solve this. So this is only of theoretical interest. Now, what's amazing is that this problem, which we can solve and is convex, turns out to have a performance as good as that hard problem. So what is this? This is minimize over x, the sum of the absolute values of entries in x, which is its O1 norm, subject to the measurements. So a very, very deep result was that this problem only also needs on the order of k log n over k measurements to exactly find x sum. And this is amazing because this is a problem we can solve tractable. This is intractable, yet there is no gap between their performance. So similar thing happens for recovery of low-rank matrices. If I want to find a low-rank matrix, let's say n by n matrix, and I have m measurements of it, m linear measurements of it, I can write down this problem. If I could minimize the rank function, which is again non-convex, horrible, etc., it would mean order of n times r measurements. By the way, these orders are basically the degrees of freedom that the object of interest has. For example, a rank R n by n matrix has only 2nr degrees of freedom. And you can do it just by count. You can take a rank R matrix, or you can factorize it into product of two matrices of size n by r and r by n. And you can get the order that way. This means, by the way, with high probability, we will see later exactly what high probability is. But essentially, with high probability, for the purpose of this talk, means probability that goes to 1 exponentially as the number of measurements grows. So it will be something like e to the minus constant times this n. 1 minus that is the probability of success. So very high probability. Now the convex problem corresponding to that one, which you also may have seen, parallels basically this problem. We went from cardinality to L1 norm. Here we go from rank to this norm of the matrix known as trace norm or nuclear norm or Shatton 1 norm, different names in different areas, which is the sum of the singular values of the matrix. I didn't write that detail down, but it's the sum of the singular values of the matrix. And this is a convex problem. It can actually be turned into a semi-definite program. Or there are other efficient algorithms to solve it. Now, this problem also needs, in terms of performance, only needs order of n times r measurements. And I don't know if I said it, but r is the rank of the task. I should have written up there. So again, there is no gap between the performance of this tractable problem and the corresponding untractable or intractable. And so this problem has gotten a lot of attention in recent years. There's a lot of work on this in different variations. This is an example of the different, so we talked about a couple of norms, L1 norm and nuclear norm. And this is an example of different, the unit norm was corresponding to some of these norms. So for example, this one is the unit ball of the L1 norm in 3 dimensions. This one is the unit norm of the nuclear norm of a 2x2 symmetric matrix plotted in 3 dimensions. And that one is the L1 or unit ball of the infinity norm, and this is a different object related to permutations. So, okay, so basically the reason things work for the recovery problems is related to geometry of these norms. So in this talk, we'll not go into the geometry, but I have the picture here, so if you're interested, you can ask later. Questions? Questions?
Yeah, I'm a little bit confused as to why you're calling the number of degrees of freedom performance. Like, why is that performance for you? Like
Why
the
is it
number
n
of
times
sam-
r for a matrix?
No, but why you're referring to it as performance? Like the fact that these
Okay,
two
performance in
problems.
the sense that if this is a recovery mechanism, how much information do you have to give to your recovery mechanism for it to work? If you have to give it a lot of information, I call it performance back. It needs a lot. Because if your degrees of freedom is n by n, and you give it n squared piece of information, of course, there's no question. It's easy to just invert your measurements and find the matrix. So the less measurements a method needs to recover, the better. That's why you call it performance. And the thing is here, this hard problem needs this many measurements to work exactly, meaning the minimizer of this function is exactly x0. And this one, which is a tractable problem, needs on the same order. There's a constant that is different between these, so it's not the same number, but the order and the way they're scaling with the dimension and the rank is the same. So we're interested, in some sense, we are interested in compression, how little information is enough. Okay, so another way to think of this problem, maybe actually a little bit more familiar to people in machine learning, is that you can also write it as some kind of a loss function acting on your gx minus b. For example, it could be a regression problem, and this would be the least square, L2 norm squared of gx minus b. And then you have certain regularizers acting on this vector x that promote different types of structure in your solution. So this is when you talk about simultaneous structures. Perhaps I should put this like after the next slide. But in any of the optimization problems I write, we can also turn it into this, rather than having the linear constraint like that as a constraint and the norm up here, you can also write it in a regularized form. And that when you have a loss and you have regularizers. Okay, so in this talk we are going to show a result. Is somebody waiting? They are? Okay. Bye. Okay, so the type of result that we will be discussing in this talk is going to be simultaneous structures. So in the set of applications, we know more than one piece of information about the object that we want to recover. For example, it is both sparse and norm. So for example, consider a matrix that is n by n. And we know that the matrix has a low rank, so rank is r, much less than n. And we also know, let's say, that it's block sparse. So only a k by k submatrix is non-zero, and everything else is 0. So in this particular case, the matrix is as if you have a k by k small matrix that's embedded inside a big matrix of all zeros. And it also has a low rank, so that k by k block also has a rank. I'll give an example of where this will come up, but that's the type of structure we'll consider it. And so the hope is that when we have more than one piece of information about the object, this additional information should help us reduce the number of measurements we need. Right? So we hope that we get something with better performance and better efficiency. At least that's the hope, so we will see if it works out. A motivation for that specific sparse and low rank problem I just mentioned comes up in signal processing. It's a classic signal processing problem called phase retrieval. In this problem, you are making linear measurements. So I'll do this very quickly. But you are making linear measurements of a signal by taking inner product with some vectors AI. However, after you take that measurement, you take the absolute value of that. Means that you lose the sign of the measurement. Or if it's a complex signal, complex numbers, then you're taking the magnitude of complex numbers. So you're losing the phase. So you have basically m phaseless measurements of the underlying signal. And you know the signal is sparse. How can you recover the signal? Now this problem deviates from the whole compressed sensing setup because the measurements are no longer linear because of this absolute value. But there's a very interesting trick that can turn it into a problem in which the measurement still is linear. And that is, I am going to introduce a matrix that is signal-signal transpose. So it's a rank 1 matrix that is outer product of the original k-sparse signal and its transpose. This matrix X is now both rank 1, following from this, and it is block sparse because this guy had only k non-zeros. So now that I have this new variable capital X, which is a matrix, I can rewrite these measurements like that, and they will be linear in the capital X. Why? Because I can write this as AI transpose X naught transpose AI, and the middle thing is just matrix X. So now I'm linear in the matrix X. So the problem becomes equivalent to this. Find the matrix subject to linear observations on the matrix. The matrix is PSD, positive semi-definite. All of the eigenvalues are positive, and the rank is 1. And this problem has gotten some recent interest in compressed sensing, but the history of the problem actually goes back to very early 60s and so on. Okay, so this is one application in which a matrix being ranked 1 on block sparse comes up. So here's a summary of our results. So we'll give a theoretical analysis of general simultaneous structures. We'll show that the performance of combined convex penalties, which I'll define later, we'll show that that performance has a fundamental limitation. So we show a lower bound on basically how bad the performance is. And then we look at the special case of sparse and low rank matrix recovery problem, which I just mentioned. And we will then, for that problem, look at how a convex recovery works, how non-convex recovery works, similar to what I showed you for L1 and sparse signals and low rank matrices. And we show that there's a gap, unlike what we saw in previous cases. So that's our goal. When you have simultaneous structures, how would the similar approach people use in other cases work or not work? And what can we prove about it? So in order to do this, we are going to build a very general theory of simultaneous structures. And I'm going to start by giving one definition, which is a certain class of norms, which I call decomposable norms. Actually, it's not definition, it's not new, it actually has been used already in these 3 papers with slight variations to each other. But the definition is as follows. A norm is decomposable at a point X if there exists a subspace T and a vector in that subspace such that the subdifferential of the norm at point X decomposes into 2 parts. One part, so everything in the subdifferential, has its projection onto T equal to E, and its projection off of T, like on the orthogonal complement of T, has a bounded norm in the dual norm. So it sounds complicated, but actually there's one more condition also on this projection. But in fact, it's actually intuitive if you think about it in the known norms. So for example, this is the unit ball of the L1 norm. So in 2 dimensions, I have a vector. Consider this vector. It is 1, 0. And that means that it's 1 sparse. So it has 2 entries, 1 of them is 0. At that point, this is the unit ball of L1 norm that crosses through that point. And at that point, the E vector that satisfies this is going to be simply sine of X. So it's going to be the vector 1, 0. So it's this red vector shown here. So it's the E is basically our typical notion of sine of a signal. Plus and minus 1s wherever entries are plus or minus 1. So this is E. The subspace T in this case is just this whole axis. So it's the subspace that contains E. And basically it's a subspace that my desired vector X also lies on. So it's the structure subspace basically. So that's T. And also known as support. So this is the support, and this is E, And then this is T perp, so perpendicular orthogonal complement to T. And we are saying that every element in the subdifferential, which are these vectors, these are the vectors in the subdifferential, they all decompose into the E component and a component along this line, such that the length of the component along that line in the dual norm, which in this case is infinity norm, is less than 1. So it's basically a certain decomposition property over the desired subspace your signal lies on and your orthogonal complement. If you think about it in terms of regularizers and so on, it's basically you can think of as this as a desired subspace or model subspace, and this subspace as some kind of deviation subspace. And you want to build penalties that penalize the deviation in an appropriate way to lead to correct recovery. Okay, so if norms that have this property, the property might seem strange, but basically all norms we use have this property. Let me show you. Yeah, so this is the L1 norm. Nuclear norm also has it. A few of the other norms I showed you also have this property. And L1-2 norm, block-sparse norms, and things like that. Okay, one more constant definition. Associated to the norm that we are looking at, we define this constant kappa. So kappa is going to be n, ambient dimension, over dimension of t, dimension of your signal subspace. The energy in the sign vector, so that's L2 norm of E squared, over L squared, where L is this quantity. It's simply the Lipschitz constant of the norm. It is how much does the norm change relative to change in its argument. Change in the argument is measured in L2 norm. So the largest change in the value of the function over whenever the arguments change. So that's L, that's the Lipschitz constant. So we define this because it comes up later. However, it's actually an interesting constant, and I'm calling it a constant because in many cases it actually really does reduce to being a constant. So for every specific norm, you have to compute it, right? You have to find the t and the e and plug it. But for L1 norm, it's going to be 1. That's easy actually because this dimension is going to be k, and this is going to be square root k, and this is going to be square root n, and the value is going to be 1. And for the L1-2 norm, it's also 1 if you compute it. And for nuclear norm, it is not a constant, but it's always bounded between a half and 1. So for my purposes, we are going to think of kappa as a constant. So now, simultaneously structured models. So this is all the definition we need to talk about to give very general result about all types of simultaneous structures. So I consider a family of norms, from 1 to tau, that are all decomposable at the desired signal or object I want to find. And we also allow for extra constraints on the model that are given by a convex cone. So for example, in the base retrieval problem, this is crucial because this is a set of PSD matrices. If you don't impose PSD, things don't work for that problem. So yeah, we can allow these side constraints as well. We call extant as simultaneously structured objects with the following parameters. A whole bunch of sign vectors, each of them corresponding to each of the norms. Kappa I constants that we just defined, and we define kappa to be the minimum of those, the worst among all the kappas of all the norms. The support subspaces Ti corresponding to each of the norms. And then we define the joint support, which is the intersection of all those subspaces. And we define intersection subspace. This one you don't actually need for the purpose of this talk, but in order to take care of that cone constraint, we intersect the cone with the intersection space and take the outgoing cone, but you don't worry about it. And then we look at this quantity, the projection of our sign vectors onto this space R. So what we are doing is that each of these norms are giving you a subspace T and a sign E. And you look at basically if you project all of them into this intersection subspace, what is that projection? So this is going to help you capture how these different norms are related to each other. What's the relative geometry between them? So here's a figure that shows, one more constant. This is basically the angle of each EI with the subspace R, or the subspace T intersection. So maybe it's easier to see it in the figure. So in this figure, I have x naught, which is this point. It has two structures, one corresponding to space T1, so that's the support 1, and this is the support corresponding to the second structure. And the intersection is going to be this line, T cap, intersection of the T's. the two sign vectors are E1 and E2 corresponding to each of the structures, and their projection onto T cap is going to be these vectors, E cap 1 and E cap 2. So we are considering the individual structures by themselves and also some quantities like theta which talk about the relation between the different structures or the relative geometry. Okay, so the results are as follows. So first, we have to answer the question, what kind of optimization problem do I need to solve now? I have several structures. Each of them come with a norm in some sense. So let's just combine those norms with each other and build a penalty function. There are many ways to do that, right? So let's look at a very general one. I take an h function which is non-decreasing in its arguments and take this function as the objective. So for example, one would be a linear combination of those with different lambdas. Another option would be the maximum on those norms. Okay, so we take this general optimization problem, and for this problem, we can show the following. So remember that the question was, how big should this m for number of measurements be for the minimizer of this problem to be equal to epsilon, so that we have correct recovery. So our result, the first theorem we show is the following. If m is less than some quantity, then this program is going to fail. So x0 is not the minimizer of this program with very high probability. The probability is over, by the way, the g's, which are random Gaussian distributed indices, right? So basically that means m less than something, it's bad, it's not going to work. Now what is this something? So that's the dimension. This one is a constant that depends on the cone. In fact, it relates to the width of the cone that define the extra constraints. Then this quantity is the smallest, so among all g's in the subdifferential of your penalty function at point x0, the one that has the smallest length of projection onto the space R. So among all subdifferentials, which one has the smallest projection onto the joint space? So that's the dominating factor, right? So okay, so this is nice, but it's too abstract. We don't get much insight. Let's try to plug in some specific functions in that. So this is very general for all functions, right? I'm going to plug in some functions to see if we can get a number or a better bound, more intuitive bound. So one thing that's nice is that we can identify among that whole class of objective functions which one is best, in the sense that if that function fails to recover x0, then every function in the class I just mentioned is going to also fail. Turns out this one is the best, and actually the reason for this or the proof for this is not hard. We can easily show if there exists a solution that is not x0. Anyway, if this one does not recover, then every other function can't recover either. So what is this f-best function? The best penalty for that purpose is going to be the max of the norms. Maximum over the norms. However, there is a weight associated with them. So it's a maximum of the weighted norms, where the weight actually depends on the correct solution x0. So this is an idealistic function. This performs best, but this in practice we cannot use because we don't know the x0. However, for theoretical purposes, let's see if this even works well. Because if this doesn't, then none of the others are going to work. So now we are going to use the structure of this to simplify the bound on them. We need one more assumption, and that assumption is, remember those sign vectors when they are projected onto the intersection space? For every pair I and j, the inner product between the projected sign vectors has to be positive. So these should not be pointing in opposite directions from each other. And again, in all cases that we consider, this condition is true, this assumption is true. So it's not a bad assumption. We needed it for the proofs, but it turns out it's also a reasonable assumption to make. So if I make that assumption, then if I plug in the f-best that we said, which is the weighted maximum of the functions, or the maximum of the weighted norms, then we get this bound on m. So problem will not recover with the probability if m is less than this thing. So now we see that the kappa and theta showed up from when we defined simultaneous structures. And we see the gamma shows up that is related to the cone. Tau is just a number of structures we have. And most importantly is this term. Now this complicated term that we had here actually has a nice interpretation. It is the minimum dimension Ti. So among all the so-called spaces Ti, pick the one with minimum dimension. And the dimension of that one determines m. Now, a very interesting observation we can already make is that our object exists in all of these t's at the same time. So the object x0 belongs to the intersection of all the t's. Imagine how low the dimension of that intersection is. That dimension is this, dimension of t. Right? That can be very low. However, the number of measurements I need is not on that order. It's not on the order of how much degrees of freedom the actual object has. Rather, it is limited by the minimum over I of the dimension of ti's. So if each individual space itself has a big dimension, you're stuck with the minimum of the dimension of those guys. So this can be much higher than this. This is what we would have hoped, but this is what we get. We'll skip the first stage of this one, but that's the interesting point about this one. And when we apply this result to the specific case of sparse and no-rank matrices, for example, we can show that, we can specifically show these different numbers on this scale. So this is the number of measurements needed. This is, let's see, the matrix here is n by n. It is of rank R, and it has a k by k non-zero subplot. So the true degrees of freedom of such a matrix is R times 2k minus R. We can compute this. This is the exact value. But the order is k times R, which you might expect. There's only k non-zeros, and that's the k by k matrix has rank 1. Then, if I were able to solve this non-convex problem, in which I minimize a linear combination of rank, the number of non-zero columns, and the number of non-zero rows, it requires this many measurements. So it's k log n over k plus k times r. Overall, a small number. See, it depends mainly on k. There's no n. N is the big dimension, right? There's no n here. But if I solve the convex relaxation, if I just take rank, replace it with no clear norm, if I take the number of non-zero columns and replace with L1 norm, even if I actually impose being positive semi-definite for the matrix, it still requires an order of measurements n times r, which is much bigger. Depends on n linearly, which is the size of the matrix. So this way we can show that there's a gap between what a non-convex problem can give you and what the convex problem. So this is unlike what the performance of L1 recovery for sparse vectors and the L1 recovery for low-rank matrices. There was essentially no gap. Okay, so some more detailed results on sparsity and low rank. So there are many variations of this problem that we considered. For example, one can focus on the case of rank 1 rather than rank R, because this is of interest in trace retrieval. And if the rank is 1, we could also give the specifically sharp bounds. So let's look at one of them. This one is the non-convex problem is minimized rank, so we want x to be sparse, x to be low rank, it's actually rank 1. And we want it to be sparse, so that's cardinality, and this is rank. And I'm only imposing symmetry constraint on the matrix. And the number of measurements needed for this problem to recover x0 is this, again, k log n over k. The convex problem, corresponding convex problem, again, replace, symmetry constraint, is going to be this. M is less than, problem is going to fail if m is less than the minimum of n and k squared. So this one is sort of expected, because n is the dimension of one of the spaces. It's the dimension of this one, corresponding to the rank. It's n times r, right? And r is equal to 1, so that's n. And k squared is the dimension corresponding to the sparsity. Only k squared non-zero entries in the matrix. And notice that you're stuck with the minimum of the two spaces, 2 dimensions, not their intersection, which would have been a much smaller number. So let me show you some numerical experiments. We try to verify our bounds by running a lot of experiments on these different cases. These experiments are done as follows. So this is m, or number of measurements, and this axis is n, or the dimension of the matrix. And every point, every square in this, so we grid the whole space, m and n, and in every point in the grid, we generate a random matrix with that structure, and then we make measurements of it, and then we solve the optimization problem and check whether we recovered the correct matrix or not within a tolerance of 10 to the minus 3 or 10 to the minus 4. And we do it 25 times for every cell in the plot. And then the grayscale shows how many times it fails. So black means complete failure, white means complete success. The grayscale is in between, sometimes works and sometimes doesn't. And it's meant to capture the probability of success. So we want to see how much probability of success of the convex problem changes with n. And how does m grow with n, basically. So our theory predicted in this case, which we have a PST matrix, rank 1, K7, and n is ranging up to 60, that the growth of number of measurements with n was supposed to be n times on the order of n times r, so it's supposed to be linear in n, and that's what we see in the plot as well. And it's also interesting to see that the transition is fairly sharp between recovery and non-recovery, which is consistent with what people see in complex sensing. This is called a phase transition boundary in those cases. And another thing that we wanted to measure was, when I'm saying failure, and I'm saying that the solution of the optimization problem is not equal to x naught, do I mean it's only a little bit different? Maybe they're close or something? When it's not equal, what do you mean? What we mean is no, when we mean failure, the error is pretty big. So this plot actually shows that empirically, that this is the minimum mean square error performance of the same problem. So this is the region, so you can see that basically the shape of this overlaps quite a bit with the shape of that overall. So there is a whole region that's completely black. So failure there is really failure. None out of the 25 cases were successful. I have some other better plots also that show the other cases. So this one, for example, here x naught is positive semi-definite. It's rank 1. K is 8, and the sizes of matrices go slightly bigger, up to size 80. And again, grayscale shows probability of success over 25 runs. And here we are using this function. So in this one, we were using, by the way, minimizing trace plus L12 penalty. In this one, we are minimizing the F best, basically, which is the maximum of L1 and nuclear norm, normalized by the correct solution. So again, this is the ideal function that we can't in practice minimize because we don't know these things in practice. But because we're doing simulation, we know x naught already, so we can construct that F and minimize it. So in this case, we see something very interesting, which is, this is again number of measurements, and this is n. Number of measurements, m versus n, at first grows linearly, but then appears to kind of saturate in this plot. And this is also consistent with our bound. The corresponding bound to look at is actually this one. It's the min of n and k squared, with some constants, but the growth is going to be like that, minimum of n and k squared. So when m is less than k squared, it's growing linearly with n. But when it hits around k squared, it's going to then after that be constant because it's not growing with n anymore. So to some extent, this is showing the behavior we expect. That is the min of the two cases. And this plot shows the area in which we have 80% failure probability. So this is basically all failure. Again, it's not like when I say fail, it's just slightly different from the way it's not. It's a real fail. And another one, this example is, this is a linear combination. So this one was F best, it was the maximum. And in practice, nobody actually uses this one, and there's good reason, because it's not practical. But this is important for our theoretical analysis. In practice, what people use, if you have two structures, you use a linear combination. And you change this lambda. And you find a range of lambda that works well for your problem. So if you try that one, and here we have tuned the lambda to a good value of lambda, then again, you see the same general shape of the plot. It's not as sharp as the previous one. And also, let's see, compared to the F max, here the number of measurements needed for the same probability of recovery should be lower because this one performs better than this one. Yeah, it's hard to see, but this one goes up to around 70 and this one goes to 60 or so. So this requires less measurements.
Do you have any plots where you show the bound on the same plot as the successes and failures? Like how tight does the bound turn out to be in these cases? You know what I mean?
Yeah, we have to calculate all those constants and see. But yeah, I mean, because we are giving lower bounds, in theory, it could be that our bound is all the way low here.
Right.
Like it's only guaranteed we cannot recover below this. But in fact, it does seem to actually exactly give you this shape.
Right.
So we think it's actually close, but we haven't done the calculation of all the constants and so on. In fact, these are better. Well, we can do it. Yeah, that's a good question. We have some other plots, but I haven't put them together in the bucket. Okay, so this one, yeah, so that's the linear combination penalty that people use typically and range lambda. We also explored what happens when you range lambda. So for this problem, there's a wide range of lambda for which the performance does not change very much. But for this problem, these weights are quite sensitive, and if you change them, the performance is just not as good. So that's also one reason probably this is not used in practice. And this one is a typical one used a lot in practice. But anyway, the interesting point is, yeah, we can verify the bounds we found, and it's interesting that in practice we see that linear growth and then saturate more or less in these plots. Of course, we want to also do much larger scale problems to see what happens for larger n's. We still haven't yet because it's a bit slow to run, which brings me also to some issues that I'll discuss afterwards in future work. But so the summary is, we want to recover a model that is known to have simultaneously several structures. And in practice, people use sum of norm penalties with some weights. We showed that combined convex penalty, including the sum, and even a whole more general class of these penalties, requires many more generic measurements than degrees of freedom, or than what you would hope for. And this is in contrast with recovery with L1 and nuclear norm, which is on the order of degrees of freedom. So that's the message. And we are working on some other related things. One is that even though we motivated our problem with phase retrieval, there is one aspect of phase retrieval problem we are not addressing yet, which is the measurements that appear in the phase retrieval problem are of this form, so they're not random Gaussian matrices. But it appears that the theory can be generalized to this. There's some recent work on that. Also, another generalization is other loss functions. And another one is, can we actually prove error recovery bounds? Can we prove when recovery fails? What is the error, or how high the error is? Error is high with how high it is, with what probability, that kind of thing, which we empirically saw in our plots that the error is high when recovery fails, but we can actually give bounds. Another interesting question is, okay, so combining known penalties may not be the best thing then, but is there another approach that is good? And turns out that that question abstractly has been answered in a recent paper, in fact, called Convex Geometry of Linear Inverse Problems by Sekaran, Parillo, and Recht. And in that, they basically say if you are able to go back to your problem and define new atoms or elements out of which you want to make this new object, and then take convex hull of these atoms, then that defines a new norm for you, and that norm actually is guaranteed to perform well, like degrees of freedom. However, that's not easy to do in many cases. So for example, in sparse and rank matrices, you can think of atoms and write it down, but taking convex hull is itself a hard problem. So abstractly, yes, there is a nice answer, but in practice, maybe you can't do it, and you're just left with combining the penalties you already know. Another issue we're working on is algorithms. So if you go back to these optimization problems, how do we solve these? So these plots were generated by just plugging them into a generic optimization solver, CDX. But that's not the best way to solve these. These have a lot of structure, and we can come up with much better algorithms that will scale to large problems. So CDX has, goes up to these sizes, but can't really handle large scale. However, there are algorithms, for example, first order methods like alternating direction method of multipliers that can be adapted and applied to these, and that scales to very large problems. And we're also looking for other applications. So if any of you have anything that sounds like this or might be related, I'll be very happy to hear that. We are going to have a paper soon, but we haven't finished it yet, so it's going to be hopefully ready next week. So if you're interested in it, please send me an email and I'll send you the paper with this video. Okay, thanks a lot. Questions?
So do you have some fields for the type of machine learning problems that this is going to work best on?
Well, I guess anything that you would write in this one, these kinds of things. So you have some, let's say, I mean, this analysis needs linear measurements, so it's more like regression type of problem. But perhaps that can be generalized. But you have a loss that acts on your linear error or residue, and then you have regularizers that try to promote certain structure, and you can combine a whole bunch of them. So this particular problem I'm considering comes up when your X is, you don't have only one regularizer, which is common in a lot of cases, but you have several of them simultaneously, and you're adding them up. So that setup is very similar to what we considered. One case that we have worked on, which is not a regression problem, but it has this kind of structure, is this one actually, the sparse inverse covariance matrices. They do have the two structures that are sparse because the networks that they capture or have sparse connections, and there's also this other type of structure in them that has to do with nodes or whether nodes are very, there's highly connected node and so on. So network has two of these structures at the same time, for example. I guess some of these other older problems also are close to some machine learning problems, like if you do PCA and outliers. Questions?
So in statistics, like we just love adding convex penalty functions on top of each other to get like the perfect massive penalty that does exactly what we want. So this is definitely making me think twice about doing that. But I think there's something kind of fundamental that I don't quite understand. Like if I add two regularizers together and they're both convex, I would just call that one big convex regularizer. So is the problem that the sum is no longer decomposable? Like they're each decomposable norms, but the sum of those norms doesn't meet that decomposability definition or something?
No, decomposability is okay. Actually, one thing is that is basically that it's not the right thing because of this. Because if you were to define atoms appropriately, you go to the end. Oops. So if you were to define atoms that correspond to all of these structures at the same time, and then take convex all of those atoms. So this sentence is similar to saying I take convex envelope, if you're more used to that terminology. I take convex envelope of the ugly object like rank or partiality and I get a nice norm.
Right.
Right. But if you have several of these things at the same time, is that issue of convex envelope is not clear anymore. Just adding these guys does not correspond to convex envelope.
So the problem is that if I just add together a bunch of arbitrary regularizers like a group lasso penalty and a nuclear norm, that's no longer the convex envelope of anything. I see.
Yeah, you can think of it that way. Although I like this convex Hall better, it's more accurate than the convex envelope way of saying it. But yeah, this combined penalty doesn't really capture the intersection as we want. However, this is of interest if you care about how many measurements required to recover something. Or I guess in machine learning terms, how does your error go down with when more measurements are available? And if you don't care about that, and you have a set number of measurements, and you just want to write down a problem and tweak the lambdas to get the best out of it, that's fine. Besides, we concluded that among all these convex combinations that you can take, even though theoretically this one is better, the max is better, it's impractical. And it's very sensitive to actually knowing the solution and plugging in the right weights. So this doesn't give you a practical recipe to do it. Yes.
Does the presence of noise affect the results one way or the other to make things better, worse, or leave them basically about the same?
So noise in the linear measurements?
Yeah.
Yeah, we actually have to really sit down and do that analysis. Based on what happened with compressed sensing type results, often when this exact case works, the noisy case also works gracefully. So there do exist forms that say your error goes down, but we haven't worked out for this yet. Thanks. But thanks for the question. Yes?
Can you give an example where the convex hull idea works better than adding the nucleus? So you said the nuclear plus the sparse, you will not, it's not clear how to construct the convex hull.
Yeah.
But are there cases where you can? I'm giving an example.
So for Laurent and sparse, if you take the outer product of sparse vectors as your atom, so like 1, 0, 0, and so on. But all case sparse vectors. And then if you can calculate the convex hull of that and normalize those, take the convex hull, and then find out what norm is induced by that convex hull, then you'll be done. But the problem is you can't actually.
Great. Are there cases where you can do that?
Ah, good question. We are wondering too. In fact, that would be really interesting to find cases. So that's actually part of the future work. Can we do this? But that construction is nice and has a proof if we can do it, but, yeah. Any other questions? Okay,